Hey, my name is Ron, and I'm a Principal Research Manager at the Cybersecurity Research Center at Ben-Gurion University of Connecticut. This work was conducted in a joint research project with the security laboratories of NSC. Cybersecurity risk management includes three main phases: identification, where we identify system assets, enumerating the threat to those assets, and identify security vulnerabilities; assessment, where the threats and vulnerabilities are aggregated into attack paths, and the risk for each asset is calculated based on the impact and likelihood of all possible attack paths; and treatment, where the relevant security countermeasures are ranked to minimize the risk to the system. So why countermeasure planning is a very challenging task? The first reason is the rapid growth in the number of security vulnerabilities discovered in past decades. With thousands of new vulnerabilities discovered each month, risk management procedures must be performed automatically and continuously. The second reason is that modern networks are dynamic and extremely complex. Therefore, to capture the rapid changes in the attack surface in such complex networks, risk management procedures must be very efficient. Related work in this domain can broadly be classified based on two categories: flexibility, meaning how flexible is a method to operator preferences during the risk calculation. For instance, budget constraints. This category is important since most countermeasure planning algorithm has some assumption on the problem. For instance, the assumption that operator preferences are linear. The second category is accuracy, meaning how accurate the risk function estimates the true risk of the system. This category is important since calculating the true risk of the system can be very time-consuming. A detailed comparison with related work is presented in the paper. I will start by presenting a high-level overview of the proposed method. First, given a network scan, we use the Mulval attack graph analysis tool to generate the attack graph of the network. We then scan the generated attack graph and identify countermeasures that can be deployed to eliminate some attack paths. Next, we derive the likelihood equation for every node in the attack graph, meaning, given a node in the graph and a set of countermeasures, the equation will estimate the likelihood of exploiting an attack path reaching that node by considering the set of deployed countermeasures. Based on the risk equation and operator budget constraint, we formulate the problem of countermeasure planning as shortest path finding problem. Finally, we use the A-star algorithm with a custom heuristic function to solve the path finding problem and generate an optimal countermeasure plan. Now let's dig into the details of our method. To do so, check out this toy example that includes three hostess, a DB server, and a firewall. The DB server includes two vulnerabilities: a vulnerability in MySQL application which can be exploited remotely and result in denial of service, and a vulnerability in the Windows Server application which can be exploited locally and result in privilege escalation. In addition, the DB server runs a remote desktop server with a default username and password. This is the attack graph generated for the network using the Mulval tool. As can be noticed, the graph includes two main attack paths, starting from node number 7. The first attack path starts by gaining network access to the DB server on port 3389, which is open for incoming RDP connection. Then the adversary accesses the DB server via RDP using the default username and password. Finally, the adversary exploits the vulnerability in the RDP server to gain admin privilege and terminate the DB service. The second attack path starts by gaining network access to the DB server on port 1529. Then the adversary exploits the vulnerability in a Windows server to execute a DOS attack. The first step in the risk calculation is assigning basic probabilities to primitive predicates. We distinguish between two cases: primitive predicates that represent facts on the target system, which are always true, and therefore assigned with a probability of 1, and primitive predicates that represent security vulnerabilities, In this case, the probability is derived based on the attack complexity matrix from CVSS. Then, we recursively compute the probability for succeeding node. We start using the N node, and then for all node. Then, we can use the graph, scan it, and search for suitable countermeasure. We develop a methodology on how to model countermeasure using the data log language, which is used by Yuval. I will not elaborate on that, but you can approach the paper for more details. In this example, our repository includes 4 countermeasures: a host-based firewall, 2 security patches, an EDR that can be used to prevent the exploitation. Here we can see the result of the scan. As can be noticed, the scanning resulted in 5 mitigation actions. Use host-based firewall to close the RDP port on the DB server, patch the vulnerabilities, use host-based firewall to close the additional port that opened on the DB server, use an EDR to prevent the code execution on the DB server. Then we integrate the countermeasure as variables into the likelihood equation. Using this equation, we can calculate the likelihood given a specific deployment of countermeasure. Finally, we recursively calculate the likelihood equation for the goal. The risk of a node is equal to the likelihood multiplied by the impact of compromising that node. The overall risk of the system is the sum over the risk of all goals. After deriving the risk equation, we model the problem of countermeasure planning as shortest path finding problem. The initial node contains all possible countermeasures which exceed the budget constraint and may include redundant countermeasures. Descendant nodes are generated by reducing one countermeasure from the parent node. Edges represent the risk added to the system when reducing the countermeasure. Goal nodes are planned within the given budget. The optimization function F is defined using the value function G and the heuristic function H. The G value represents the actual risk under countermeasure plan N. The H value represents a lower bound of the risk that must be added to plan N to satisfy the budget constraint. A detailed description of the heuristic function is presented in the paper. Finally, we use the A-star algorithm to solve the problem. To evaluate the method, we use much larger network that simulate medium-sized business. The network includes multiple security vulnerabilities. We test for 2 scenarios: an internal attacker that resides in host 23 and an external attacker. We define 5 attacks on that network: access sensitive information on DB1, spoof host 12 and host 22 communication, access sensitive data on the email server, run code on web server 1, and apply a DOS attack on web server 2. Here are the possible countermeasures, their types, cost. We consider network-based firewall, host-based firewall, network-based IPS, host-based IPS, and EDR and patches. In this figure, we can see the evaluation results over different budget constraints. As can be noticed, with a low budget, the algorithm suggests patching the vulnerable software, which is cheap and reduce 70% of the risk. Then, with more budget, the algorithm suggests deploying host-based firewall to host 11 or host-based IPS to the email server to reduce the risk to zero for internal and external attacker respectively. In this figure, we can see the execution time for the 2 attackers. We compare the execution time with and without the use of risk equation, which prevent the need for recalculating the attack. As can be noticed, the use of risk equation dramatically reduces execution time. In the paper, we present an extensive evaluation of the proposed method against recent works. For conclusion, we suggest a heuristic approach for the countermeasure selection problem that consider the system topology, vulnerabilities, and interaction between them. Experiments show that our method provides cost-effective plans. Comparison with recent work show that our approach provides optimal trend in terms of risk. Thank you very much.